Section 3.6 is called Arguments and Euler Diagrams. Many logical arguments involve sets whose elements are described using quantifiers such as all, some, none. The mathematician Leonhard Euler used diagrams to determine whether arguments that involve quantifiers were valid or invalid. For example, something that looks like this. The statement all P's or Q's can be illustrated by this Venn diagram where the circle P is entirely contained inside the circle Q, and that illustrates the statement that all P's are Q's. You think of this dot inside the P circle as being a representative of some general element in P, and you can see that if it's in P, it also has to be in Q. So you can see how helpful these diagrams can be. Here's another. No P's or Q's. This time, you want the P circle and the Q circle to be separated completely so that no P can possibly be in Q. So a representative element of the set P would have no possibility of also being in the set Q. Some P's or Q's. This is a pair of overlapping circles. The circle P and the circle Q overlap, indicating there's a possibility that some P's could be Q's, also allowing the possibility that some P's might not be Q's. So a representative element of P in the lower left diagram would also be an element of Q. That would illustrate some P's or Q's, whereas in the lower right diagram, the representative element of set P is not in Q. So that illustrates the statement some P's are not Q's. You can see how these diagrams can be very helpful in thinking through these things logically. We're going to refer to these as Euler diagrams in honor of Leonhard Euler. If you're interested in him, you might want to look him up. He was a very prolific mathematician, and his life was rather interesting. In this section, we'll construct diagrams like these to determine the validity of arguments. For example, use an Euler diagram to determine whether the following argument is valid or invalid. All courses are fun. This course is a college course. Therefore, this course is fun. A couple of things about this. The first two statements above the horizontal line are the premises of the argument. Those are the things we're assuming are true. The statement below the line is the conclusion of the argument, and that stack of dots that form a triangle shape is the word therefore. So I'll read it again. The premises are all college courses are fun, and this course is a college course. The conclusion is, therefore, this course is fun. And our job here is to decide if that argument is valid or invalid. Let's use Euler diagrams to help us answer that question. If we let C stand for college courses and F stand for fun courses, because the first premise says all college courses are fun, the circle C is completely inside the circle F. So your Euler diagram would look like this. And that's the Euler diagram for all C's or F's. So if you look at a representative course in our argument, you can see that as long as the dot stays inside the college courses circle, the C circle, it will also be inside of this F circle, which are the fun courses circle. So this course is fun is a valid argument. Now, I'll mention this more than once, but when you say an argument is valid, what you're saying is, based on the premises of the argument is valid. If any of the premises are not true, then you might not agree with the conclusion that the argument reaches, but the argument itself is valid if you accept the premises. So anytime you're making this argument, it's understood that the argument is valid if you assume the premises are true. Let's do another. And this is sort of a perfect illustration of my point. The premises are all fried foods are greasy, all greasy foods are delicious, all delicious foods are healthy, and the conclusion is, therefore, all fried foods are healthy. You might say, well, all these premises aren't valid. For instance, the one that says all delicious foods are healthy. But the argument's validity doesn't depend on anything but if the premises are accepted, then is the conclusion valid or invalid? We're accepting the premises and we're working from there. You've got to keep that in mind when you're doing these argument analyses. So let's get started. If you draw the Euler diagram for this, it says all fried foods are greasy, so the fried food circle is completely inside the greasy food circle. All greasy foods are delicious, so the greasy food circle is completely inside the delicious food circle. And finally, all delicious foods are healthy, so the delicious food circle is completely inside the healthy food circle. The conclusion of this argument is, therefore, all fried foods are healthy. And you can see if you put a dot as a representative of a generic fried food, it will also be inside the healthy food circle. So the argument is completely valid. All fried foods are healthy. It's a valid argument as long as you accept all the premises. Another one. All birds have feathers. That animal has feathers. Therefore, that animal is a bird. Again, drawing the Euler diagram and labeling circles, we'll let B stand for the bird circle, F stand for the feather circle. Because all birds have feathers is the first premise, the B circle is completely inside the F circle. That would be illustrative of the statement, all B's are F's. According to the second premise, we know that the animal has feathers. So the representative dot has to be somewhere in the feather circle. It could be inside the feather circle but outside the bird circle, or it could be inside the feather circle but also inside the bird circle. And that tells us immediately that we don't know for sure that the animal is a bird. That being the case, that animal is a bird is an invalid argument because we could illustrate it either way and have a correct illustration. I will say one thing about choosing this answer when you're doing it as a multiple choice problem. When you're choosing the diagram representing the correct answer from a multiple choice list, be sure to choose the one whose dot shows why it's invalid. So the dot being outside the bird circle shows why the conclusion that animal is a bird is invalid. So be sure to pick the variation that shows why the particular argument is invalid. How about this one? Some dogs have tails. All things that have tails are pretty. Therefore, some dogs are pretty. Let D stand for dogs, T stand for tails, and P stands for pretty. The first argument says some dogs have tails. That means we're going to put an overlapping D and T circle to allow some dogs to have tails, but the possibility that some don't. The second premise says all things that have tails are pretty. That means the tail circle has to be completely inside the pretty circle. If we include a pretty circle, wherever we put it, it has to completely envelop the tail circle. So it might look something like that. If some dogs have tails, and the tail circle is completely within inside the pretty circle, that means that some dogs are pretty is a valid argument because there's no way for that dot to be in the tail circle without also being in the pretty circle. Use all the premises in the argument to determine a valid conclusion for the argument. All people have feelings. R2-D2 does not have feelings. Therefore, what? Let's come up with a valid argument by removing that question mark and putting in a statement. Starting off with the first premise, all people have feelings. So if I have a people circle, it has to be completely inside the feeling circle. R2-D2 does not have feelings, so if I look at a representative dot for R2-D2, R2-D2's dot has to be outside the feeling circle. But putting it outside the feeling circle automatically puts it outside the people circle because the people circle is completely enveloped by the feeling circle. Therefore, a logical conclusion would be R2-D2 is not a person. How about this? Determine whether the conclusion presented is valid or invalid. All people with a job work hard. All people who work hard enjoy vacations. Some mathematicians enjoy vacations. Conclusion, therefore some mathematicians have a job. Is this valid or invalid? Well, again, let's draw an Euler diagram. All people with a job work hard, so the job circle is inside the work hard circle. All people who work hard enjoy vacations, so the work hard circle is inside the vacation circle. We only know from the last premise that some mathematicians enjoy vacations, so that representative dot for a mathematician, it could be completely outside the job circle. We only know that some mathematicians enjoy vacations, so that representative dot for mathematician has to be inside the vacation circle, but other than that, we really don't know. So can we conclude that some mathematicians have a job? And the answer is, looking at the Euler diagram, no, that's an invalid argument because that representative dot representing a mathematician could be outside of the job circle. This takes practice, but the more you do it, the better you're going to get at it. How about this conclusion? Take the same three premises, which means we can use the same Euler diagram, but this time, let's look at the conclusion, therefore all people with a job enjoy vacations. Well, the job circle is completely inside of the enjoy vacation circle. Therefore, if the person is inside the job circle, they would automatically be inside the vacation circle, the enjoy vacation circle. So that conclusion would be valid. So that argument is a valid argument. Let's wrap up by talking about some real-life examples of logic. There are many everyday examples of conditional statement, and we're using those conditional statements a lot in our logic statements. For example, with credit cards. Here's a typical ad for Citibank, the Citi Simplicity card. You can read through this, but what do you get from it? I guess what I'm trying to introduce here is the idea that these if-then statements, which are the basis of our logical arguments that we've been doing, appear everywhere in real life. If you were to read this, what could you get out of it? Well, one thing you could get out of it is if you make a purchase during the intro period, then you will not be charged interest during the intro 12-month period. In other words, that's an if-then statement. They appear everywhere. But you might be required to make the minimum monthly payment to get the deal. Lots of fine print. What else might you get from this? Well, if the intro period is over, then you will pay an interest rate from 16.24% to 26.24% on unpaid balances. Again, when you read through these credit card contracts, they're just full of these if-then statements, which are the basis of our logical arguments. Other contracts such as apartment leases and automobile service plans, again, full of conditionals. They specify the responsibilities of each party. By reading your contract, you may find out things like, if you damage the apartment, then the landlord may use your security deposit to pay for damages. If nothing in the apartment is damaged, then the landlord must return your security deposit in full. Again, a series of if-then statements inside of a typical contract. Medical insurance. This is extremely important, but it can be terribly complicated and very confusing. Here's some basic things about medical insurance that might be helpful. Medical insurance plans can include coverage for general checkups and medicine. If you have non-routine costs, then plans typically include deductibles. The deductible is the amount that you must pay out of your own pocket, before your insurance will begin paying costs. For example, if your deductible is $8,000, then you must pay $8,000 in costs before your insurance will begin paying the remaining costs. An example, you enroll in a medical insurance plan with a $5,000 deductible. So far this year, you have paid $1,500 in medical costs and now need a surgery that will cost $8,000. How much must you pay before your medical insurance begins paying for the surgery? Well, think about this. Your insurance begins to pay at $5,000, but you've only paid $1,500 so far. So if you subtract, you can see that you have to pay an additional $3,500 before your insurance will kick in and begin to pay. How much of your surgical costs will be covered by your insurance? Well, think about it. Your surgery cost $8,000, and from the calculation we just did, you know that you've got to pay $3,500 of it. So $8,000 minus $3,500 is $4,500. So $4,500 of your surgical costs will be covered by the insurance. You'll be responsible for the rest.
All right, so today we're going to do the last logic section, and we're going to talk about arguments and Euler diagrams. So we're going to use diagrams to help us decide whether arguments are valid, and then we're also going to apply that to some everyday real-world stuff. And I do actually mean legitimately real-world things. All right, so first, Euler diagrams are basically like Venn diagrams in some sense. And so they're like Venn diagrams, like the set theory stuff that we did at the beginning of the semester. And like I said, they help us determine whether arguments are valid or invalid. And so we're going to have some different statements that have associated pictures. So we have all P's are Q's, no P's are Q's, some P's are Q's, and some P's are not Q's. Okay, so let me go ahead and draw the pictures associated with these. So we've actually talked about the statement all P's are Q's before. This really means P is a subset of Q. Okay, so when we draw our picture, we'll have P. Okay, so there's, oh gosh, that's not a circle. There we go, that's better. So we have P, okay, and I hope I have cords plugged in here, so hopefully they're not, let me move a little here. Hoping they're not too loud. There we go. Okay, so we've got P's, and we're saying that all P's are Q's, so Q has to be a bigger circle. Anything that's in P must also be in Q. So the way that we sort of denote that is we draw a representative dot. So we say any dot in P must also be in Q. Okay. All right. Now the picture for no P's or Q's is if you have a circle for P, here's something in P, and we're saying that anything that's a P can never be a Q. So you're going to have two completely non-intersecting circles. So Q is completely outside of Q. They can never have anything in common. So those are the two extreme cases where you've got either one is entirely inside the other or they're not even touching at all. So the sum is going to be the in-between case. So if you have some P's or Q's, then you're going to have the two circles and they'll intersect but not all the way. So we'll have Q here, here's P. And the way that we'll denote that some P's are Q's is we're going to put a dot right inside the middle. So that dot in the middle is the thing that says some P's are also inside Q. Oops. So there's stuff in the left circle, and it can also be in the right circle at the same time. So similarly, we can have some P's are not Q's. So the picture for that will again be your circles. They'll intersect but not entirely. And the way that we'll show that some P's are not in Q is we're going to draw a circle, a little dot on the left. So this dot is illustrating that the way these circles intersect, some P's are outside Q. Not everything in P has to be inside Q. So we have these four pictures. They're a little messy looking back on it now. But we're going to use these types of pictures to help us analyze arguments. Okay, so let me do some examples here. So we're going to be asked for most of these homework problems. Use an Euler diagram to determine whether the argument is valid or invalid. And so first, we're going to have what we'll call premises. So here are two premises, and basically, for the purposes of these problems, we're going to assume that the premises are true. Now, we may or may not agree with them, but we're just going to assume they're true. So the two premises we have here are all college classes are challenging classes, and that this class is a college class. Okay. Now, the next part of the question is going to be that this class is challenging, and this last sentence here is the conclusion. And so basically what the question is asking when they ask whether the argument is valid is they're asking, must the conclusion follow from the premises? So if we assume that this class is a college class, and if we assume that all college classes are challenging classes, can we conclude that this class must be challenging? And last notational thing before I do the problem, this symbol with the triangle, that is a symbol which means therefore. Okay. All right, so we're going to use an Euler diagram, and what we're going to do is use the diagram, use the circles to figure out whether the conclusion must be true. So we'll start with the first sentence. The first sentence says that all college classes are challenging classes. So that's that first type of picture, where we've got college classes, and they are a subset of challenging classes. So in other words, there may be other classes as well that are challenging, like high school classes, but definitely all college classes are challenging. And then the second sentence says, this class is a college class. So our class is inside college. And we want to know, can we conclude that this class must be challenging? And the answer is yes. Because the way we've drawn the picture, C is inside the, quote, challenging circle. My pen's lagging just a little bit behind me here. So C is inside the challenging circle. It has to be if it's in college. And therefore, this argument is valid. That is, we can definitely say the conclusion has to be true with this premise. Okay. All right. So we're going to have several of these examples where you have to draw the picture and use the picture to figure out the validity. So here's another argument. So all tired people drink coffee and I drink coffee are the premises. And then conclusion, I am a tired person. So let's step by step draw the picture for this scenario. So we'll have our Euler diagram, and that is Euler for the pronunciation there. And we're told all tired people drink coffee. So tired people are a subset of all the people in the world who drink coffee. And again, we're assuming these premises to be true. Now, the second sentence says, I drink coffee. And given that, we want to know, must it be true that I am a tired person? Now, on the previous problem, there was only one place that the dot could go. But here we have a couple options. So if you drink coffee, or if I drink coffee rather, I can either be in like the donut ring, or I can be inside the tired circle. So I could be, crucially, here. And if I were there, rather than inside the tired circle, then I wouldn't be a tired person. So I could be outside the tired circle. It is not guaranteed that I'm a tired person. In other words, I might be the kind of person that drinks coffee just because I like the taste, not necessarily because I'm tired. And so that means that this argument is invalid. So we put the dot in the place that illustrated how the conclusion might be false. Put it in the donut ring. Okay. Alrighty. Let's do a couple more here. Yeah, I'll do a couple more and then I'll let you guys do one. All right. So, another argument. So we've done all. Now let's do an example with some. So we're told some paintings in the Louvre are by Da Vinci. The Mona Lisa is a painting in the Louvre. Therefore, the Mona Lisa is by Da Vinci. Now, the previous examples have had kind of silly premises, but these are legitimate premises, so it is true that some paintings in the Louvre are by Da Vinci, and it is also true that the Mona Lisa is in the Louvre. At least at the recording of this video, that is true. So, let's go ahead and draw our picture. We'll do this step by step. So we've got two categories. We've got paintings by Da Vinci, and we've got the, there we go. We've got the paintings in the Louvre, and because it's some, that's where you have like the intersecting circles. And we're told that the Mona Lisa is a painting in the Louvre, where again, we have this ambiguity, so I could either put the Mona Lisa in the right part of the red circle or the left part of the red circle. So to illustrate that the Mona Lisa doesn't have to be by Da Vinci, I can put my dot here. There's the Mona Lisa. So the Mona Lisa, again, could be outside the Da Vinci circle. It doesn't have to be, but it could be. And so the argument is invalid. Okay, so you put the dot, when there's an ambiguity, you put the dot in the place that illustrates how the conclusion may not be true. Now I expect some of you may be objecting to this because the Mona Lisa is by Da Vinci, so the conclusion is true. But that's not what we're asking here. So note, this statement is true. I'm so sorry that the slides keep doing that. There we go. This statement is true. Yes, the Mona Lisa is by Da Vinci, but the question is not asking whether conclusion is true. It's asking, with the premises that we have, those first two sentences, with those premises, can you conclude the Mona Lisa is by Da Vinci? And the answer is no. Those two premises are not enough. So the statement is true. You know what? I'm gonna write over here maybe. But the reasoning is not sound. Okay, so what we are gauging here is the reasoning. Is the reasoning good? And the reasoning with these two premises and the conclusion is not. Okay, so. All right, let me do one more and then I will let you guys do one. So we haven't had an example with no yet. So no children like clowns. All creepy people like clowns. And we're assuming these premises to be true. Can we conclude that no children are creepy? So let's draw a picture for this scenario. So first sentence, no children like clowns. That means that we've got children, oops, and they're off to the side, and they are entirely separate from the circle of people who like clowns. They do not intersect. Okay. Now the second sentence says, all creepy people like clowns. So that is an all statement. And so that means that we're going to fit creepy people inside the larger circle of people who like clowns. So we actually have 3 circles here. We've got children and liking clowns. That's from the first sentence. And then the second sentence introduces this third circle, creepy people. All right. And now we're trying to figure out, can we conclude that no children are creepy? Well, if you're a child, there's only one place that you can go. You're going to go in that circle. And if you're there, then you definitely can't be inside the creepy circle. You're way outside of that. So C must be outside the creepy circle. And therefore, this argument is valid. If we assume the premises to be true, then the conclusion will work. Okay? All right, so let you do an example real quick. So you're just going to want to sketch an Euler diagram to represent this argument. So all prime numbers are odd. 2 is a prime number. Therefore, 2 is an odd number. Okay, so pause this video real quick. Take a minute to draw that picture. And then when you're ready, you can press play. Okay, all right, so let's take a look at this. It's really weird doing these one-sided videos. Okay, so you may be a little confused by the conclusion. 2 is not an odd number, and it is not true that all prime numbers are odd, but just remember that we are assuming that the first 2 sentences are true, and with that, trying to see whether we can make the conclusion. So let's go ahead and draw the picture. So we've got all prime numbers are odd, so we have the prime numbers, it's the all circles, so we've got prime inside odd. Okay. Prime is a subset of odd. And you're told that 2 is a prime number. So there's only one place that 2 can go. There's no question here. So 2 goes there. And so this should be kind of what your picture looked like. And I didn't actually ask you, but with this, can we say that the argument is valid or invalid? And since where we've drawn the 2, that is in the odd circle, that means that the argument is valid. And again, of course, 2 is not an odd number, but the argument is valid, so that would tell you that the premises must not be accurate. Okay. So this one, there is no ambiguity about where the 2 could go. It had to go in the blue circle. But let me go back here. And I might avoid the top of the screen because that seems to be more glitchy than the rest. So, a lot of people ask me, where does the dot go? Like, it's kind of confusing as to where do you put the dot. So let me try to summarize that based on these examples. So either you put the dot where it must go. So for some of the problems, like the ones that, like the one that you just did, the 2 had only one place it could be, and then you put the dot there. So that's easier. Now, if you're in the case where the dot could be in 2 different places, then you use the dot to illustrate that the conclusion may be false. Okay, so like in this, or actually this one wasn't also one. So in this example and the one after that that you did, the dot could only be in one place, but like in the Mona Lisa example, it could go in 2 places, and we put it intentionally in the place that illustrated how the conclusion didn't work. Okay? All right, so I've just got one more type of example, and then I'll do some real world examples of logic. So previous examples was all determine the validity of an argument. Here, we're not going to have a conclusion, but we're going to use the premises to make a good conclusion. So we're going to find a good one. So all chocolate contains cocoa solids. That is a true premise. White chocolate doesn't contain cocoa solids. That is also a true premise. So let's draw the picture of this and try to figure out from the picture a good conclusion here. So first sentence is that all chocolate has cocoa solids. So we've got chocolate. I did not plan my picture well here. We've got all chocolate is inside the bigger circle of being a food which contains cocoa solids. So that's the first sentence. And then the second sentence is that white chocolate doesn't contain cocoa solids. So if it doesn't contain cocoa solids, that means there's only one place it can be. It has to be outside of the red circle. So it's out here. And so from this, and you probably could have figured this out without the picture, you can conclude that white chocolate, so therefore, white chocolate, whoa, that was weird. White chocolate, there we go, is not chocolate. And that is also true. White chocolate is not chocolate because it's outside the chocolate circle. And this is really by the definition of chocolate. So white chocolate does not contain cocoa solids. In fact, it only contains cocoa butter. So it is not actually chocolate, which blew my mind when I first learned that. But you can use the picture to help you figure out a valid conclusion for the premises. So again, let me let you guys try one of these type problems. So here we will have, yeah, okay. So here we'll have multiples of 8 are divisible by 2 and 4. 475 is not divisible by 2 or 4. So pause the video for a sec and try to figure out a valid conclusion for this argument here. right. So let's go ahead and take a look at this. And again, I think you could probably figure out if multiples of 8 must be divisible by 2 and 4, and 475 is not divisible by 2 or 4, then you can conclude that 475 must not be a multiple of 8. Okay, so that should be pretty evident, I would think. But just in case, let's draw the picture real quick. So, your box, multiples of 8 are divisible by 2 and 4. That would mean that you've got your multiples of 8. They are inside the circle of being divisible by 2 and 4. And if 475 is not divisible by 2 or 4, then it has to be out here somewhere, and therefore 475 cannot be a multiple of 8. It's not in the multiple of 8 circle. Okay? So that's the first main part of the homework, which is all of the Euler diagrams, all the kind of Venn diagram questions. But now, let me just take a few minutes here to talk about some real life stuff. And I do truly mean real life things. So we've been doing all this logic. We talked a little bit about the fallacies in the 3.4 section. And it turns out that, we've been spending all this time talking about conditionals, and that is because there are many everyday examples of conditionals, especially if you remember all those different forms of the conditional. And so what we're going to look at are credit cards, contracts, and medical insurance. We're going to look at these 3 different scenarios. And the biggest thing I can say here is, if you take nothing else from this section, you should read contracts very carefully. And depending on sort of where you are in terms of establishing yourself, you will have read some number of contracts. And the more you read, the more you'll see that there's just lots of stuff in there that you have to pay attention to. So let's look at credit cards first. All right, so many credit cards advertise a 0% intro APR for the first some number of months. And so APR, we'll talk about this a little more actually in a later section, but it stands for annual, don't know what happened there, stands for annual percentage rate. And basically what this is that it is a fee if you don't make payments on time. So if you don't pay your credit card bill in full at the time that it is due, then you get charged a fee. And the fee is based on your APR. And as you might guess, a higher percentage APR means a higher fee. The higher your APR, the higher the fee that you get charged. And that fee is in the form of interest. So we're not really talking about interest yet in this chapter, but we will in the financial section. And so here's an ad that I found online for an actual credit card. It's a Citi credit card. And it was advertised to me as one of the good ones. Okay, so notice that there is an intro purchase APR. You have 0% APR for 12 months. So if you're late on your payments for the first 12 months, you have 0% interest. And then notice you've got 0% APR. Sounds good. But down here, you have an APR, 16.24% to 26.24%. And it is variable. So when they say you have a variable APR. What that means is that the company can change the rate. Not sure why the slides keep doing that, but sorry. I know that's annoying. So the company can change the rate. And realistically speaking, it's not usual that rates go down. They usually go up. So the company can change the rate and charge anywhere in that 16.24 to 26.24 range. So I promise you that this is going to have to do with logic, and it does. Because what does this really mean? It means if you are late on your payments for the first 12 months, then you will not be charged interest. Notice if then, it's a conditional. And if you are late on your payments after 12 months, then you do get charged interest, and you can be charged any rate between the 16.24 to 26.24%. And these are very high interest rates. The highest interest rate that you can possibly get charged is 29.99, and so 26.24 is pretty high up there. And so this is really just to highlight that this is an example of something that you see in your everyday life. Most people have a credit card, or at least have seen people use them, certainly. And so the point here is that when you see things like 0% intro APR, there's an underlying conditional associated with the ad, which kind of makes it less desirable than the ad was probably trying to make it be. Okay, so there's an example of conditionals. So now let's look at some contracts. So contracts such as apartment leases, automobile service plans, things like that. I'm sure you can think of many others. They are full of conditionals all over the place, and the conditionals basically specify what each party is responsible for. And so again, I'm going to do this in red, the big takeaway here for the contracts, just regardless, is that you should always read it. Even though they tend to be rather long and boring, you should read. And not only should you read, you should also ask questions. You should ask them to clarify what they mean by the different parts of the contract. And you especially want to pay attention to all the fine print, all those details that they have in the contract. Make sure you understand exactly what it is that you're getting into. So here's an example of what you might see in a contract as relates security deposits. So when you move into an apartment, you give the landlord a security deposit, and they're supposed to pay it back to you pending certain conditions, hence conditional. And so this is really what you would see in the contract in some form or other. So if you damage the apartment, then the landlord may use your security deposit to pay for damages. So like if you have, I don't know, water leakage, or if you put a bunch of paintings up and you have lots of holes in the wall, then the landlord can use your security deposit to pay for those things and give you what's left, if any. And then if nothing at all in the apartment is damaged, then the landlord has the responsibility to return your deposit in full. So this is what you should see in probably more complicated language in your contracts with the landlord. Now, there is some fine print here, of course. So you have to be really careful that you read the contract, because depending on the way it is worded, a landlord can charge for prior damages, i.e. damages that you did not cause but were there when you moved in, unless you show that they were there. before you moved in. So at least I assume this is typical, where when you are moving into the apartment, they first give you like a checklist that you have to return within a certain amount of time and say, yes, these things were all in good condition, or no, there were some things that were wrong at the time of moving in. And then that's supposed to protect you from being charged from like your previous person living in the apartment being a slob, or breaking things or whatever. So this is something you should not take lightly. If you have something in your apartment that is in any way damaged at all, and it doesn't hurt to be really nitpicky, it's your money that you're talking about here, take pictures of anything that is wrong and have a written record of that. So whatever it is that, oh my goodness, whatever it is that may be damaged here. And not only should you have a written record, you should keep it. Keep a copy for yourself. So there's another example of contracts which have hidden conditionals within them. Okay, so just one more scenario I want to go over here, and that's medical insurance. So, medical insurance plans generally include coverage for certain things, different things for every plan. But things like, you're allowed one annual checkup for like normal physical stuff, one dentist appointment every 6 months, things like that. And you can have coverage for medicine. You can get a discount or a certain plan that lets you purchase prescription meds. And then for non-routine things, the big stuff like a surgery, for example, plans generally include, so I'll write that down, non-routine, meaning, for example, surgery. Plans also include deductibles. And the deductible tells you basically how much money must you pay to pay for the surgery or whatever before the insurance company will pay for the costs. So for example, if your deductible, again, here's the conditional, if your deductible is $10,000, then you must pay $10,000 in insurance-related costs before the insurance company will chip in with their money. And so you can guess from this that a lower deductible is nice, okay, because you have to pay less before the company will help you out. But life is rarely black and white, right? So it's maybe nice because that's a perk of the plan. But because it has that perk associated with it, that means that generally those plans cost a lot more per month. So you pay for, you get what you pay for. So if you want to have that perk where in a disaster you are covered and you don't have to pay as much, if you want that perk, you have to pay more per month to have the privilege to own that security, basically. So I've just got one last example before we're done for the day about deductibles. So let's say you enroll in a medical insurance plan with a $5,000 deductible. And thus far this year, you've paid $500 in insurance-related costs. And now something happens where you need a surgery. And the question is, how much money must you pay before your insurance starts paying for the surgery? And basically here, we have to pay the rest of the deductible. So you have to pay the rest of your deductible. And they've given us the two monetary amounts here. So you have a $5,000 deductible, and you've used up 500 of it. So the stuff we have left to pay is 5,000 minus 500, which is equal to 4,500. So for this surgery, you have to pay $4,500 before your insurance will contribute. And then the other side of that question is, okay, you're paying $4,500. How much of the surgery will your insurance pay for? And they will pay for whatever's left. So they will pay the remainder of the $8,000. Oops. So I'm looking here at the amount of the surgery that was specified. So you have an $8,000 surgery and you paid $4,500 of it, and therefore the insurance company will pay $8,000 minus $4,500, which is $3,500. Okay. So there's a more calculation-based example for these real-world logic things. So on your homework, you can expect to see some scenarios to look at, multiple choice kind of stuff mostly. And just hopefully this gives you something to sink your teeth into where, yes, these conditionals do actually come up in the real world, and they do make a significant impact on your life decisions. Okay? All right, so I'm going to stop there.